All right. So we've got a problem here. It says it wants to determine the slope and displacement at the midpoint of the beam. And you've given values of E and I. So I know we've talked about this already, but let's just mention it again. Right now, the only two techniques we have for displacement are direct integration and conjugate beam. And you might recognize right off that if I tried to use direct integration on this, first of all, I wouldn't be able to write a continuous moment equation. I probably have one that's good from 0 to 9, and then a second one that's from 9 to 12. And then handling the integration constants would be a little challenging. So you could do it. There's no question you could do it. But I think a more efficient approach now would be to do conjugate beam. Now the first step in conjugate beam is to, we need the moment. Now you can do that a couple different ways too. You could actually write the moment equation and plot it. But I'm going to go back and do a more traditional graphical technique. I'm just going to draw the shear moment diagram real quick. So to do that, I'm going to start, just like we did for the first exam, is I'm going to assume that I have a positive shear at A and a positive shear at B. And remember our sign convention for shear, if it causes your structure to try to rotate clockwise like this, then that's positive. And you can see that up on the left and down on the right causes that clockwise rotation. So those are both positive shears. So the first thing I want to do is I'm going to find those values. So I'll come over here and I will sum moments at one of these connection points to find the other reaction. I'm just going to sum moments at A, just starting on the left side alphabetically, and set it equal to 0. That'll check for equilibrium. So summing moments about A, I have my 5 kip load. What kind of moment does that create about A? Positive or negative with right-hand rule? That's negative moment. So that'll be the force is going to be 5 kips, and the distance from A to the force is 9 feet. And then my shear at B creates what kind of moment about A? It's also negative. So it will be the shear at B times its moment arm, which is 12 feet. So I should be able to solve for the shear at B. It looks like, I don't know what that is. That's 45 divided by 12. What's that? It's not a nice, neat number, is it? 2.75? 3.75? And it should come out negative. So the shear at B is negative. And then if I sum my forces in the y direction, make sure they're in equilibrium, I should be able to solve for AY. So I'm assuming up is positive, so my shear force at A is up. My shear force at B is down, and my load is down. So plugging my minus 3.75 in here to B, minus minus cancels, makes it positive. It looks like my shear at A would be 1.25 kips, positive. Okay? Any questions about that? So now let's just draw our shear moment diagram. So I'll make a little template. There's my starting point. There's my ending point. I know something's going to happen underneath that point load, so I'll put a line in my template for that. Go ahead and establish my positive x-axis, my positive shear, and all my units for shear will be in kips. So looking at the starting shear, what do we have? Well, my shear at A is 1.25. So that's positive. 1.25. Now remember, the change in shear is equal to the area under the load curve. There is no load. So if I'm going to start at 1.25, I'm going to end at 1.25. And also remember, the slope of the shear diagram is given by the load. And the load is 0. So here's 0 slope. So basically I have constant shear over the first 9 feet of 1.25. Now, as you go from the left side to the right side underneath this point load, how much does your shear change? 5, the exact amount. And that's down, so that's negative. So 1.25 minus 5 brings me to minus 3.75. The change in shear over this range should be the area in the load curve, which is again 0, so no change. And that's great because you can see we end up with the shear that we computed it to be. And the slope of the shear diagram is given by the load. The load is 0, 0 slope, straight line. So there's our shear diagram. Now we'll finish this off by now constructing the moment diagram. So again, I'll establish my positive x-axis, positive moment. This will be in kip feet for my units. We look at the starting moment, which would be the moment at A. It's a pin, so I've got no moment, 0. I've also got a pin at B, so that should also end with no moment. So I kind of know where I'm starting. I know where I have to end. So let's look at this first 9 feet. The change in moment here is the area into this part of the curve. It's a rectangle, so that area is base, which is 9 feet times 1.25. I think that's 11.25. Is that right?
Yeah, that's right.
So I'll come out to be 11.25. The slope of the moment diagram is given by the shear, and you can see the shear value is constant and positive. So here's a constant positive slope. The change in moment over the last 3 feet is the area in this part of the shear diagram. I'll double hatch that. That's a negative area. 3 times 3.75, which is negative 11.25. That brings us to 0. That's great. Matches our endpoint. And the slope of this part of the moment diagram is given by the shear, and the shear value is constant, so constant slope, and it's negative. So we get a nice triangular bit there, and there's our moment diagram. So that's about halfway through the problem. So now what I'm going to do is apply this moment diagram to the conjugate beam. So the first thing I want to do is come over here and construct my conjugate beam. Now the conjugate beam, remember the conditions from the real beam to the conjugate beam. So let's examine our beam. We have 2 external supports. One's a pin, one's a roller. Well, in conjugate space, they don't change. So my conjugate beam is going to be the same thing. My pin is going to stay a pin, and my roller is going to stay a roller. Now just to remind you, remember if this was a free end, it would have become fixed. If this was a fixed end, it would become free. If these supports were internal, they would turn into hinges. Just remember, those are our 3 cases. So there's my beam. And now I'm literally going to lift up this moment diagram, and I'm going to plop it right down onto my beam. This is a positive moment, so I'm applying it as load. Which way is positive load, up or down? Up. So this is going to be a positive load. It's going to look something like this. And what is that value going to be? Well, it's going to be the moment, which is 11.25 kip feet. And in conjugate space, we take the moment and we divide it by EI. So that becomes the intensity of the triangular load on our conjugate beam. And just to give you the spacing, that's 9 feet and that's 3 feet. Everybody see that? Now all I have to do is solve this problem. What do I want to solve the problem for? Well, the original problem wants the slope and displacement at the midpoint. Well, the midpoint is right about here at 6 feet. So I want the internal value of shear and moment in the conjugate beam, and that will tell me the slope and displacement in the real beam. So ultimately, I want to find the internal shear force and bending moment here at the middle of this beam. In fact, I think what I'll go ahead and do is I'll just kind of sketch that point out, and I'll say that's 6 feet over. And that'll help us plan what we're going to do next. So if ultimately I'm trying to find the shear force and bending moment at this section, what side do you want to work? Do you want to work the left side or the right side? Yeah, I think you can see the left side is going to be a lot easier to deal with. So if I'm going to just do the left side, I probably only need the left side reaction. So let me draw that on there. So here is positive shear at A in the conjugate beam. This would be positive shear at B in the conjugate beam. But the only one I'm interested in is this one. Everybody see that?
Yes.
Okay.
VA.
Sorry?
VA is the only one here.
Right, because when I cut this structure, I'm going to look at the left side, and I won't need anything but the reaction at A. Yeah.
Now, when you do the conjugate beam, is VA still the same as VA in the regular beam?
No, this is the VA for the conjugate beam.
Just double check.
Now remember, shear in the conjugate beam is what? It's slope. So when I solve for this shear in the conjugate beam, I'm actually finding the slope at A. So sometimes if I ask you for what's the slope at one of the supports, it could be a fairly simple conjugate beam problem you have to solve. All right, so with that in mind, let's figure this out. So I didn't give myself enough space to visualize all this, so let me do this. I'm going to redraw my beam, and I'm just going to put the bits on it that I want to keep track of. So I still have my shear at A and my shear at B. And what I'm going to do is I'm going to take this part of the triangular load, the triangle that has a base of 9 and a height of 11.25 kip feet EI, and I'm going to find that force. Okay? So I'm going to call that force 1. And the other little triangular piece here, I'm going to call that force 2. Now, I'm probably going to want, I know I want shear at A, so I'm probably going to sum moments at B, so I'm going to look at my distances to my forces this way. Okay? So let's figure out what the force at 1 is. Well, 1 would be, I'll just kind of box this area in. That's my 1. So it's a triangle. Area of a triangle is 1/2 base times height. So 1/2 base, which is 9 feet, times the height, which is 11.25 kip feet, divided by EI. So what's that going to be? Somebody's going to have to help me with that. That's going to be a strange number. While you're figuring that out, I'll go ahead and calculate F2, which is this part of the triangle, which would be 1/2 base. This base is only 3 feet, and it's the same height, 11.25 kip feet divided by EI. Anybody get the first number?
You want EI, this is EI?
Well, just leave the EI as EI. Don't divide by EI yet.
50.6.
50.6? 50.625. And I'm going to run out of space here. See, kip feet squared And then what's the other one? It'd be a third of that.
28.1.
Say again?
28.1.
I like that better.
Yeah, 16.875.
16.875? Let's see if I can squeeze that in there. And again, that's going to be kip feet squared over EI. So I've got feet times feet, that's why I get the square, and then the kip. Let's see. See where I can put this in. So what do you think D2 is? What's the distance from B to the centroid of this triangle?
2.
It'll be 2/3 the distance, right? So that'll be 2. So I'll write those here. I'll write D1 and D2. So D2 will be 2 feet. What's D1? Well, I have to come over 3 feet, and then the distance from here to the centroid is 1/3 the distance, which is another 3 feet. 3 plus 3 is 6. Everybody see that? So now I have all the pieces I need to find my shear at A.
So you take the moment at B?
That's what I'm going to do. So let's do that. I'm going to sum moments at B and put it equal to 0. So about B, both F1 and F2 create what kind of moment about B? Positive or negative? Negative, right? So I'm going to have minus F1 times D1 minus F2 times D2, and then the shear is going to create what? Also negative. That's going to be minus the shear at A times 12. So we should be able to solve for the shear at A. I'll let you put all those numbers into that and tell me what the shear at A should be. I have a feeling it's going to be negative. So we've got 50 times 6, which is about 300. We've got 16 times 2, which is about 32. So that's like 332 divided by 12. It's going to be like 20-something. 28, 29, I'm guessing. 28.125, and that's going to be kip feet squared over EI.
Everything divided by 12?
Sorry? Yeah, everything divided by 12.
I get it.
So now that I have this, I can actually cut the structure. So I'm going to do that here. So here's going to be my free body diagram for the cut section. So I'm going to draw that. I'll draw it a little bit bigger so it'll have some room. So this will be 6 feet long because we're cutting this left side. I've got my shear at A, which I solved. Now see, positive was up. I got a negative value, so it's actually down. So it has a value of 28.125 kip feet squared divided by EI. There's the reaction. Internally, I'm going to have positive shear at the cut and positive bending moment at the cut. Also, I have that portion of my triangular load. So I've got to figure out what this intensity is here of this load. You go back to the original one, at 9 feet it was 11.25. So what's it going to be at 6 feet? Well, those are similar triangles. Right? 11.25 is to 9 as what is to 6? Well, 6 to 9 is 2/3. So what's 2/3 of 11.25? 7.5. So this becomes 7.5 kip feet divided by EI. Everybody see that? So for that piece, I'm going to need an additional force, which I'll call F3, which is the concentrated equivalent of that. Let's see if I've got some room for that over here. So what is F3? What will be the area of this triangle? So it's 1/2 base, which is 6 feet, times height, which is 7.5 kip feet over EI. That's 22.5.
Yes, sir.
So 22.5, and that will be kip feet squared over EI. And this distance, what's 1/3 of the distance? The distance is 6, 1/3, so this should be 2 feet. So now I've got everything I need to find the shear and moment in my conjugate section, which will map back to the displacement and slope in the real beam. So I don't know if I'm going to have enough room to fit all this in here, but we can try. So let's sum moments at the cut, like we do every time. So looking at the sum of the moments here on this section, we start with the moment. That's a positive moment. About the cut, F3 creates what kind of moment? Positive or negative? Negative. So I'm going to have negative 22.5 kip feet squared over EI. That's the force times a distance of 2 feet. And then the reaction down here, that creates positive moment. That would be positive 28.125 kip feet squared over EI. And that's times 6 feet. So what is the moment equal to? It looks like it's going to be negative, and I'm guessing somewhere around 50 or 60. I'm guessing. You got 22 times 2, and that's negative, and 28. You got what? Well, 6 times 28, that's only about 180. And you subtract 50, you should get about 130. Anybody getting about that?
123.75.
That sounds okay to me. You got that too? Negative, right? 123.75, and that's going to be kip feet cubed. So we can first take stock of what we have here. Moment being negative maps to displacement being negative. Does it make sense that here in the center point we would have a negative displacement? I think so. In fact, I can probably guess that my displacement will look something like this. So you can see in the middle you would expect negative displacement. Seems reasonable. So now I just have to compute this by dividing by E and I. So let's do that. So we now know that the displacement really maps over to the moment, which is equal to this minus 123.75, and that's kip feet cubed. And I'm going to divide all that first by E, which is 30,000 kips per inch squared, divided by I, which is 800 inches to the fourth. Now I've got inches and I've got feet, so I need to do a conversion. So 12 cubed is 1728, so there's 12 cubed inches in a cubic foot. What's that? It looks like it's going to be pretty small. So 0.008. Anybody else getting that?
Yeah,
0.008. Give me one more decimal. 9. So basically 9 thousandths of an inch. Not a lot, is it? Now think about this. This is a beam that's only 12 feet long. Look on the floor. Count 12 tiles. That's a pretty short beam. Right? It only has 5,000 pounds on it. That's not crazy. If you drive a truck, you're probably driving a 5,000 pound truck. And the moment of inertia is 800 inches to the fourth. That's a stout beam. So that seems reasonable. If you'd have got, a foot, you'd know something's wrong. Okay? So keep that in mind. I barely have enough room to do the shear, but we'll squeeze it in, see if I can make it fit. So we'll go ahead and sum the forces in the y direction, and that should give me the shear. So I'm going to assume up is positive, so my shear is down minus the shear. My force 3 is up, that's positive, so that would be plus 22.5 kip feet squared. This is really getting tight down here, sorry about this. And then my reaction is down minus 28.125 kip feet squared over EI. So you put your shear to the other side. It's basically just the difference in these two. It comes out to be negative, right? And it's just going to be, I don't know, what's 28.125 minus 22.5? It's pretty small. 5 point what? 5.625, and that's going to be kip feet squared divided by EI. Now, if you go ahead and divide that by E and I and convert the cubic feet to the feet squared to inches squared, you're going to get a really, really, really small number. But does it make sense that it's negative? So when I'm out here at the center point of my structure, that means my slope is still going down. It's still negative. So I haven't found the maximum displacement yet. But it's getting pretty close because eventually it's going to go to 0. That's where the maximum displacement is. And then it'll go back up positive. So I think that sign seems reasonable. I'll let you figure that out. I've really run out of space here. I didn't manage my space very well in this problem. I apologize for that. I know I messed up. I have all this white space up here. I got to start cramming it more on the top to start. Terrible. It's terrible. So any questions?